Hi guys, welcome to this video. Let's get straight into things today. So I've got a problem to have a look at from this book. Probability and statistics with reliability, queuing and computer science applications. So rolls off the tongue, doesn't it, that one? The author is Kishor S. Trivedi. Okay, it's quite an old book by the looks of things. I can't actually remember what, I think somebody gave me this book a long time ago and I've referred to this several times. It's really good for kind of intermediate kind of level probability and statistics. So it's not an introductory book necessarily, but it doesn't really get into the fine details. So it's a good book to refer to. But there's some interesting problems in here as well, and one of them I've selected for what we're going to be having a look at in this video. So we're on page 184 in this, and so you're going to need to have some familiarity with continuous random variables, expectation of continuous random variables, cumulative distribution functions, how they're related to the density function of a continuous random variable, and what else? Integration by parts. Okay, we're going to be using integration by parts to do some of this. Okay, so as long as you're comfortable with those kind of ideas, which I'm not going to be going through in detail in this video, then we can have a look at this problem. Okay, so what's the problem? Using integration by parts, show that for a continuous random variable x, we've got the following: that the expectation of x is equal to the integral, and let me get this right, from 0 to infinity of 1 minus f of x dx plus, is it plus or minus? I think it's minus actually, isn't it? Minus the integral from minus infinity to 0 of f of x dx. Okay, assuming that all of these, this, and this are all finite. Okay, so we've got no problems with these blowing up to infinity or anything like that. So using integration by parts, show that for a continuous random variable, this equality holds, assuming that expectation of x, this integral and this integral are all finite. Okay, and it goes on to say, this result states that the expectation of a random variable x equals the difference of the areas of the right hand and left hand shaded regions in figure 4.p.1. So the figure shown is something like this. Okay, so we've got this. So this is figure 4.p.1. So this is the graph of f of x, which is the cumulative distribution function, and therefore we've got on the one hand this area, and then we've got this area. Okay, so this is this area here, this is this area here, so it's the difference of those two areas which is going to be the expectation. That's actually not something that we need, that's just an interpretation of this. That's not something that we're going to need to use for this. And by the way, that's 1, that's at height 1. Okay, so it took me a while to figure out the solution to this problem. It's actually marked up as a difficult problem, if I remember rightly. So page 184. Yeah, it's got an asterisk next to it. So that means that it's a difficult problem. Actually, it's not too difficult. But as with any problem really, any challenging problem, the difficulty is just finding the right perspective to view the problem from. The difficulty is often not at the actual calculations and things like that you have to do. It's actually just finding the right mindset, the right way to view the problem. And that was the case here with this one, okay? Because the natural tendency here, especially when it says use integration by parts, the natural tendency is to start here, okay? Why is that? Because expectation of x for a continuous random variable is the integral from minus infinity to infinity of x times f of x dx, where f of x is the density function. F of x, by the way, capital F of x is the cumulative function. So because of the form here of expectation of x, which is this, it's natural to go straight into this using integration by parts. Okay, if you do that, you end up with some difficulties. So let's have a look. So, for example, we need to assign u and dv by dx. How are we going to assign them? Well, we're forced really to assign dv by dx to the density function, because we need this cumulative density function, right? I don't want to be differentiating this, really. I need to be integrating it to make sure that I get this f of x in here. So then, on the other hand, we've got u, and well, what am I going to have to do? I'm going to have to differentiate that. Du by dx equals 1. So this is going to be equal to u times v, x f of x. I mean, that kind of looks like it's going to be a bit of a problem. Minus the integral of v times du by dx, f of x from minus infinity to infinity. Dx. Okay, I mean, kind of looks like there's something there, because this is, I've got the f of x here, but the limits are wrong. I suppose I can split this up. I could get this out of here, but then I'm going to get the integral from 0 to infinity of f of x dx, and there's all sorts of difficulties. In particular, this thing here. I'm told that each of these are finite, but I'm not told anything about this thing here. So I can't just say, well, that's finite as well, because it might not be, right? So this was the first thing that I went into doing, kind of naively. It doesn't really lead anywhere, okay? Unfortunately. And it turns out that the problem is, we don't really want to be starting over here and using integration by parts on this. We want to be using these expressions over here and using integration by parts on these expressions. Okay, so how does that work? So let's take them one at a time. Integral from 0 to infinity, 1 minus f of x dx. Now we use integration by parts on this thing. Okay, u dv by dx. But which way around do I assign these things? Because it doesn't even look like a product. Well, it kind of is. So you might have seen this trick before when it comes to, for example, using integration by parts to find the integral of natural logarithm of x, where you think about it as 1 times the natural logarithm of x. Yeah? Okay, so we're going to do that. We're going to think of dv by dx as 1 and u as 1 minus f of x. So du by dx is going to be equal to minus f of x. Remember that d by dx of the cumulative distribution function is the density function, and therefore v is going to be equal to x. So this is going to be equal to u times v, so x times 1 minus f of x, between 0 and infinity, minus the integral, I left myself enough space, have I? The integral of v times du by dx, so that's going to be plus x times f of x dx from 0 to infinity. Okay, well, this is going to be equal to, because f, capital F, uppercase F, is a cumulative distribution function, that means that the value of f at infinity, or the limit, is going to be 1. So when I plug these limits into here, I'm going to effectively get 1, in fact, let's do it this way, 1 minus, And then when x is equal to 0, this is going to be equal to 0. Sorry, 0 minus 0 plus the integral from 0 to infinity of x f of x dx, which of course is just equal to the integral from 0 to infinity x f of x dx. And I know that this is going to be finite because I know that expectation is finite. Okay, and this is kind of half of the integral, so to speak, of expectation of x. Okay, so the expectation of x, remember, is the integral from minus infinity to infinity of x f of x dx. I'm not saying it's got half the value, it's just I'm integrating over half of the range of possible values of x. The expectation is from minus infinity to infinity of x f of x. Here I'm integrating from 0 to infinity of x f of x. Okay, so then on the other hand, we've got integral of minus infinity to 0 of f of x dx. Do the same thing, right? U equals f of x, dv by dx equals 1. du by dx is f of x, use it, oh, I've rubbed it off now. V is equal to x, so this is going to be equal to u times v, x f of x between minus infinity and 0, minus the integral of v times du by dx. This is where it starts to get a bit more obvious where things are going to go, because if that's one half of this integral, so to speak, this is kind of the other half. So this is equal to, when I plug x equals 0 into here, this is going to be 0. Plug infinity, minus infinity into here, so because again, uppercase f is a cumulative density function. The limit as you go down to minus infinity is going to be 0. So this is going to be 0 minus 0 minus the integral from infinity to minus infinity to 0 of x f of x dx. Okay, so therefore this thing up here, where can I write it? Let me write it, let's write it down here. So the integral from 0 to infinity of 1 minus f of x dx minus the integral from minus infinity to 0 of f of x dx is equal to, this we found was equal to the integral from 0 to infinity of x f of x dx minus minus x, so that's going to be plus the integral from minus infinity to 0 of x f of x dx. Just for clarity, that's equal to minus the integral of x f of x dx. Should have wrote that out, but I didn't. And both combined, both of these are going to be finite because we know that expectation is finite, but these actually are the expectation of x. Okay, and that's it. Okay, problem solved. Okay, so nice little problem, nice short, sweet little problem. But again, the natural tendency is to kind of start on the left-hand side of an equation and try to work towards the right-hand side. It doesn't always work that way. In theory, yes, you can always go in that way, but in practice, sometimes it's going to be easier to go from right to left. And once you've figured out how to go from this side to this side, then it becomes a bit more clear how you can get from this side to this side. But there's usually some step involved that would be very difficult for you to. When you see it going in that direction, it's easy for you to see how you would go in that direction. But actually going in that direction in the first place is quite difficult. Okay. So anyway, that's my solution to this particular problem. If there's anything that you're not clear about, please leave a comment in the comments section. Please don't forget to hit the subscribe button. Give this video a like. It'd be really appreciated if you show your support. So that brings us to the end of this problem, and it brings us to the end of this video. Thanks for watching.